All right, welcome. Today we are diving deep, and I mean really deep, into the stuff that makes up, well, pretty much everything. We're going to be talking about quarks, the fundamental building blocks of the matter all around us. You ready to crack open the secrets of the universe? Let's do this. So let's kick things off with a question that totally stumped physicists for decades. We all know atoms are made of protons, neutrons, and electrons, right? And electrons, as far as we can tell, are fundamental. You can't break them down. But what about protons and neutrons? If you could somehow crack one open, what would you find inside? That's the big mystery we're going to solve today.
And to get to the bottom of it, here's our game plan. Think of it as a little study guide. First, we'll see how scientists brought order to a chaotic particle zoo. Then, we'll meet the amazing building blocks they found, the quarks. After that, we'll check out the super clever, colorful solution to a huge quantum puzzle, meet the whole family of quark flavors, and finally, we'll tackle the biggest head-scratcher of all, why you can never, ever find a quark all by itself.
Okay, Chapter 1, Organizing the Particle Zoo. So, back in the mid-20th century, physicists were smashing atoms in these giant accelerators, and they started finding a flood of new, totally bizarre particles. It was awesome, but also a complete mess. There was no rhyme or reason to any of it, or so it seemed. Now, most of these new guys belong to a group called hadrons. That's just a fancy name for any particle that feels the strong nuclear force, the superglue that holds the nucleus of an atom together. Protons and neutrons are the most famous hadrons, but suddenly there were dozens more, and it was getting crowded.
So how did they sort through all this chaos? Well, the big breakthrough came from a physicist named Murray Gell-Mann. He came up with this brilliant organizational system that he playfully called the Eightfold Way. Think of it like the periodic table, but for hadrons. He started grouping them into these really neat geometric patterns based on things they had in common, like their quantum spin.
And just look at this. This is a pattern for one group of hadrons called baryons. It's like a constellation, where every single particle has its perfect spot based on its electric charge and another property they called strangeness. I mean, a pattern this beautiful, this elegant, it just can't be a coincidence, right? It was a huge clue that these hadrons weren't fundamental at all. They had to be made of something even simpler.
And that beautiful pattern leads us right to the next big question, and to our second chapter, the building blocks called quarks. If these hadrons aren't the bottom level, then what are the fundamental ingredients? What are they made of?
This is where Gell-Mann and another physicist, George Zweig, both had the same incredible idea. They proposed that there must be these new, truly fundamental particles out there. Gell-Mann called them quarks. The idea was that these were the basic Lego bricks, and you could combine them in different ways to build all of the hadrons in the zoo.
So at first, they suggested three types, or flavors, of quarks: the up quark, the down quark, and the strange quark. And here's where things get absolutely nuts. To make the math work for those patterns, these quarks had to have fractional electric charges. I mean, think about that for a second. Every single charge ever measured in history was a whole number. This was like finding a 2/3 of a person. It was a completely wild, almost unbelievable idea.
But with these strange new particles came some surprisingly simple recipes. For example, baryons, like protons and neutrons, are all made of 3 quarks, and another type of hadron, called a meson, is made from 1 quark and 1 antiquark. Simple rules which could create all that amazing diversity.
Let's actually see how it works. Let's build a proton. The recipe calls for 2 up quarks and 1 down quark. So let's do the math on the charge. You take a plus 2/3, you add another plus 2/3, and then you add a minus 1/3, and what does that equal? It equals exactly +1, the perfect whole number charge of a proton we see in the real world. It worked.
Okay, so the model is looking great, right? Well, not so fast. This brilliant idea immediately created a brand new, massive problem. A really deep quantum puzzle that needed its own, equally brilliant solution. And that brings us to Chapter 3, a colorful solution.
So here's the puzzle. There's this super important rule in quantum mechanics called the Pauli exclusion principle. Basically, it says that 2 identical particles called fermions, and quarks are fermions, can't be in the exact same state at the same time. It's like a cosmic 1 per seat rule. But wait a second. Our proton recipe calls for 2 identical up quarks. How on earth is that possible without breaking one of the most fundamental rules of physics?
The solution was to propose yet another new property, this one called color charge.
Now, let's be super clear here. This has nothing to do with the colors you and I see. It's just a fun, memorable name for a new kind of charge that quarks carry. It comes in 3 types, which they called red, green, and blue. So now those 2 up quarks in a proton aren't identical anymore. One can be a red up quark, and the other can be a green up quark. Problem solved.
And this new property came with one huge rule. Any real particle you can actually observe has to be colorless or color neutral. It works just like mixing light. When you combine red, green, and blue light, you get white. Well, to make a baryon, you need 1 red, 1 green, and 1 blue quark, which makes the whole thing color neutral. This elegantly explained why we only ever see particles made of 3 quarks, or a quark and an antiquark. Those are the combos that work.
So, the theory was looking stronger than ever. But just when physicists thought they finally had it all figured out, you know how this goes, the universe had a few more surprises up its sleeve. Which brings us to Chapter 4, a full family of flavors. As particle accelerators got even more powerful, they started finding particles that just didn't fit the 3-quark model. And it turned out there weren't just 3 flavors of quark. There are 6. Here's the whole family photo. Up, down, charm, strange, top, and bottom. The charm, strange, top, and bottom quarks are all much heavier and less stable, which is why it took so long to find them. But this is the complete set. And that brings us to our final chapter. And honestly, this might be the weirdest, most mind-bending part of the whole quark story. If quarks are real, and all the evidence says they are, then why has no one in any experiment ever seen a single one all by itself? This is the great confinement puzzle. The answer is a fundamental law of nature we call quark confinement. And it's exactly what it sounds like. Quarks simply cannot exist on their own. They are permanently locked up or confined inside of hadrons. They're on permanent lockdown in their little particle homes.
So what happens if you try to pull one out? Okay, picture this. You reach into a proton, you grab one of the quarks, and you start to pull. The strong force holding it together acts like this bizarre cosmic rubber band. The farther you pull, the stronger it gets. So you pour in more and more energy, stretching that bond until the energy becomes so huge that, bam! Thanks to Einstein's E = mc squared, that energy literally turns into matter. A brand new quark and antiquark pop into existence out of pure energy, and they instantly pair up, so you're left with 2 brand new hadrons instead of 1 free quark.
My favorite way to think about this is with a simple bar magnet. You know how a magnet has a north and a south pole? Well, if you cut it in half, you don't get a separate north pole and a separate south pole. You just get 2 new, smaller magnets, and each one has its own north and south. It is the exact same idea with quarks. You can't break one off by itself. You just end up making more complete hadrons.
And there you have it. We've kind of reached the bottom floor of reality as we know it. The 6 quarks, along with electrons and their cousins, these are the fundamental particles that build everything we see and touch in the entire universe. From that chaotic particle zoo, we arrived at this picture of incredible, elegant simplicity. All of this amazing knowledge is wrapped up in what we call the Standard Model of particle physics. It's one of the most successful theories in the history of science. But I'll leave you with this final thought. Is this it? Is the Standard Model the final chapter in the book of reality? Or, just like the Eightfold Way was a clue to something deeper, is the Standard Model just another beautiful pattern, hinting at an even deeper, stranger truth that we haven't even begun to discover?